We're going to dive into 6G, and here's the spoiler. This isn't really about faster download speeds anymore.
Not at its core, no.
I mean, while you're still waiting for 5G to hit every corner of your city, the next generation is already being standardized, and its mission is far more revolutionary. It's about turning the global mobile network into a massive, high-resolution sensor.
That really is the crux of the vision. We've synthesized this deep dive from the core ITU standards documents, the framework setting the global direction, and from some leading academic research on optical tech.
Okay.
So our mission today is to understand how 6G, which is formerly known as IMT 2030, really transforms the network from, let's say, communication only to a system that deeply integrates communications and sensing.
Okay, let's unpack this. You've got this huge 6G vision defined by 6 core pillars: global coverage, strong security, things like that. We're going to zone in on 2 of the most disruptive ones. The use of all spectra, which means light, and the delivery of all sense applications, which is all enabled by AI and sensing.
Exactly. This deep dive is really your shortcut to understanding the 2 major enabling technologies for the network of 2030.
So let's start with the blueprint, the timeline. 6G has to build on 5G, but you mentioned it does more than just make things faster. What are the new metrics that define success here?
Well, 6G certainly enhances 5G's 3 big scenarios, broadband speeds, low latency, and massive connectivity. But the truly important part is what it adds.
Okay.
The network now has to be judged on entirely new key performance indicators.
Sure.
Things like highly accurate positioning, the network's inherent sensing capacity, and its intelligence level. It's moving beyond just being a simple conduit for bits.
So it's becoming, what, a proactive entity, one that understands its environment.
Precisely. It understands its environment and location with extreme precision. It's a shift from connecting people to connecting and perceiving the world.
That sounds like a long road to roll out. When does the industry actually plan to switch on this perception layer?
So this is all managed by the International Telecommunication Union, the ITU. They approved the core framework for 6G, that's the IMT 2030 framework, way back in late 2023.
So that set the stage.
It did. And now the industry is expected to submit detailed technical proposals for the radio interface technology in early 2027.
So we are talking about a full roadmap leading right up to the end of the decade.
Correct. The consensus in the industry is that the first version of 6G standardization will probably be released right around 2030. And, underpinning this entire timeline is AI.
Of course.
We're seeing AI computing power doubling far, far faster than Moore's Law ever did. So 6G networks are designed to harness that intelligence.
To what end?
The aim is for fully automated, proactive management. It means the network constantly optimizes its own resources and adapts to environmental changes, all without human intervention. The network literally manages itself.
Now, for the biggest challenge, fuel, if we're going to support all that intelligence and sensing capacity, we need massive bandwidth.
Yeah.
And the traditional radio spectrum is, well, it's packed.
It is. You mentioned the all-spectra pillar, and that's exactly why we're turning to light.
Why? I mean, what's wrong with the spectrum we have?
The existing radio frequency band, the RF band we use for everything, is almost completely exhausted, and it's heavily regulated. It runs up to about 300 gigahertz.
Which isn't enough.
Not even close. To handle the monumental traffic demands of 6G, we're talking petabytes of data from sensors, holography, and beyond. We have to look much, much higher on the spectrum.
And how much higher does the optical band go?
It is astronomically larger. The optical band runs from 300 gigahertz up to 30 petahertz.
Wow.
That range offers literally thousands of terahertz of available unregulated spectral resources. It's the new frontier.
Thousands of terahertz. That's staggering. And that's where optical wireless communications, or OWC, comes in? What specific part of this massive spectrum is the industry targeting first?
The key to this is terahertz technology, often just called T-hertz. It operates between, say, 0.1 and 3 T-hertz. This range is crucial for getting those ultra-high data rates over short distances.
What kind of applications?
Things like wireless data centers or even prototypes that are already testing data rates over 100 gigabits per second.
Okay, but OWC uses light, which brings up an immediate concern. Light needs line of sight, right? Doesn't that make it unusable if you, put your hand in front of the signal? Or if a wall's in the way?
That's the critical question, and it's exactly why OWC is a complement to traditional RF, not a replacement. And when we talk about OWC, we are really talking about two primary technologies, each for different applications.
Walk us through those.
So first, you have visible light communication, which you've probably heard of as Li-Fi.
Li-Fi, right?
It uses the LED lighting that's everywhere for both communication and illumination at the same time. It's secure, it's high speed, and very energy efficient, mostly for indoor internet and IoT.
And I've heard it's really good for positioning indoors.
It is. Because the light source is fixed, VLC provides much better indoor positioning accuracy than GPS. It doesn't suffer from signal blocking or that multipath interference you get with radio waves indoors.
So, Li-Fi is for secure, dense, indoor spaces. What about for longer links?
That's where free space optical, or FSO, comes in. This typically uses infrared laser diodes for long-range, point-to-point links.
Like fiber optic speeds, but through the air.
You can think of it that way. It can achieve fiber-level throughput across huge distances, even connecting continents or cities. This tech is absolutely crucial for what we call non-terrestrial networks.
You mean like satellites?
Exactly, connecting satellites to ground stations.
So aside from pure speed, what are the big practical benefits of using light for all this?
Well, the environmental ones really stand out. OWC supports green communication because it leverages energy-efficient LEDs that are already lighting our spaces.
Right.
Plus, you can integrate solar cells into the link to act as both the optical receiver and as energy harvesters. It's also vital for places where radio waves are hazardous or just disruptive, like in chemical plants or hospitals.
Because there's no electromagnetic interference.
Exactly.
The spectrum problem is solved. But speed is useless without a purpose. So what are the amazing full sensory applications this new bandwidth unlocks? This brings us to that all senses pillar.
This whole layer starts with something called integrated sensing and communication, or ISAC.
ISAC.
Yeah, it's the integration of perception and communication systems to share both wireless and hardware resources. Essentially, the entire network, your cell towers, your access points, it's repurposed to act as a giant, high-resolution sensor array.
So wait, instead of installing separate radar or LiDAR on every street corner, the network infrastructure itself is collecting the sensor data.
Precisely. It generates information like high-resolution locations, velocity, Doppler shift, and even detailed images.
How detailed are we talking?
Prototypes of these 2 Hz ISAC systems have demonstrated the ability to achieve millimeter-level resolution imaging of objects that are currently occluded.
Occluded? You mean the network can essentially see through things?
That's one way to think about it, yes.
Millimeter-level imaging through the air? That is a massive capability leap. What applications could possibly demand this level of performance?
They are entirely new ways for us to interact with technology. Take the tactile internet, for instance.
The tactile internet?
This requires not just high speed, but ultra-low latency and extreme reliability. We're talking down to the microsecond level to enable real-time applications like skill transfer.
Where you instantly learn a physical task.
Yes, or remote physical examinations, or even complex remote robotic surgery.
That's a huge responsibility for a network. And I assume we're moving beyond just flat video calls, right?
Absolutely. We're moving to holographic communication, real-time 3D images that require just massive bandwidth to transmit resolution, color, 3D tilt, angle, position data, all simultaneously.
A communication experience that matches reality?
That's the idea.
And then the concept that feels the most futuristic.
Yeah.
Directly controlling devices with your mind.
The wireless brain-machine interface, or BCI. This allows the transmission of brain signals to electronic devices, think of your smart home, or medical equipment, enabling users to control them using only their thoughts.
That's the next logical step in integrating humans and machines.
It is.
But with all this complexity, all of this data being created by sensing and BCI, how does the network stop itself from immediately collapsing under the data load?
That leads to a really fascinating concept. Semantic communication.
Okay.
It's a novel AI-driven approach that moves past the traditional bottleneck of needing to perfectly transmit every single bit. Instead, it focuses on extracting and encoding only the meaning.
The semantic information.
Yes, only what's relevant to the service. So if you're communicating the urgency of a medical alert, the network focuses on the meaning, not on the flawless transmission of every pixel or waveform. It dramatically improves efficiency for human-oriented services.
We've painted this incredible picture of intelligence and light, but none of it happens without a solid physical foundation. So let's look at the infrastructure needed to carry these massive data streams.
It all starts with the physical connection to the tower. We are already deep into a paradigm shift called fiber to the antenna, or FTTA.
Right.
This is where high-capacity optical fiber runs all the way up the tower to the antenna's electronics, replacing the older, heavier, and distance-limited copper coax cabling.
What are the biggest payoffs of running fiber right up the mast?
You get dramatically longer distances, up to 20 kilometers between the base station and the antenna, and significantly less power consumption.
How so?
Because the electronics at the top can be cooled by ambient air rather than needing expensive air conditioning units at the base. It's just lighter, cleaner, and faster.
Fiber sounds ideal, but we always hear stories about how delicate it is. What's the biggest vulnerability in managing these optical connections in the field?
That's the crucial operational constraint. It's contamination. Simple dirt, dust, or oil is the biggest issue.
Really? Just dirt?
It's estimated to be the #1 cause of troubleshooting problems for 95% of installers in optical networks. Dirt on a connector surface causes massive signal loss. This is why mandatory proactive inspection is non-negotiable before every single connection is made.
That attention to detail is intense. Okay, now let's look at the more advanced architectural components that make the environment controllable, as 6G promises.
We need new ways to manage and steer these radio waves, especially those high-frequency THS signals. The most exciting component here is probably reconfigurable intelligent services, or RISs.
RISs, what are those?
Think of them as programmable digital mirrors.
Programmable mirrors for radio waves.
Exactly. These are 2D metamaterials, often made of things like liquid crystal or graphene, that can dynamically manipulate an electromagnetic wave that hits them.
So they can reflect it, steer it.
They can reflect it, steer it, or perform beamforming to enhance coverage and avoid obstructions. They essentially turn physical infrastructure like walls and ceilings into smart network extending components.
And what about the antenna arrays themselves?
We're moving to ultramassive MIMO, which is basically the expansion of current antenna arrays to hundreds or even thousands of antenna elements.
And that does what?
It improves spectral efficiency, so more data in the same space, and it significantly boosts that 3D positioning accuracy we need for the sensing capabilities we discussed earlier.
And finally, the structural change to how the network actually defines a coverage area.
Right. That's the cell-free or cell-less architecture. Instead of today's traditional cellular grid, which often has poor quality at the edges of the cell.
We've all been there.
We all have. This approach distributes massive access points over a wide area, and they jointly serve users seamlessly. It effectively eliminates that boundary effect, providing a much more consistent, reliable user experience everywhere.
Now, to handle the ultra-high frequencies of terahertz, we must be talking about entirely new chips and materials, right? Silicon can't handle that.
Absolutely. To fabricate integrated circuits that can operate up to or even above 1 terahertz, we are enhancing silicon technology with advanced platforms that integrate electronic and photonic components side by side. The material science really has to catch up to the communications vision.
We have covered the monumental ambition of 6G, the convergence of light, pervasive intelligence, and integrated sensing, all driving toward a cohesive global network. And it's defined by the ITU's 2030 standardization schedule.
It is. It's a network that perceives the world, enabling applications that were previously just science fiction.
It's a complete paradigm shift.
It is, but realizing it requires comprehensive real-world verification. We need massive test beds that are capable of validating these TDP's level peak rates and the microsecond level latency.
And integrating everything.
Exactly. Integrating complex components like cell-free MIMO and RIS all together. It's an engineering challenge on a scale we haven't seen since the initial rollout of 4G.
Which brings us back to the ultimate trade-off. Since 6G relies on this massive proliferation of intelligence, and AI computing doubles far faster than traditional technology, it raises a key question. While optical wireless communications promises energy efficiency for the communication part, what are the ultimate power consumption costs and environmental demands? I'm talking about both energy and the new advanced materials for TX chips and the massive AI-driven cloud and edge computing needed to sustain a global, intelligent, all-senses network where the network itself is constantly sensing and learning.
That is the energy footprint we must begin to calculate now.